So, you are discussing about the crystal symmetry. So, just I took the example of cubic crystal, and for that I was explaining what are the symmetry elements, and that elements I was showing in case of cubic crystal. So, for the timing you forget the translational symmetry. Let us concentrate on the other three symmetry: rotational, symmetry or symmetry of rotation. Okay. So, we found that different axes of rotation, there are many axes of rotation. Okay. With respect to that axis, those axes, if you rotate the crystal, you will have the symmetry, but there are difference in how many fold of symmetry for different axes. So, we have seen this basically 3 axes of rotation, 3 axes of rotation, 3 axes of rotation of 4-fold symmetry, So, this 3 axis passing through the center of the face, this axis passing through the center of the face, and then we have seen these 4 axes of rotation, 4 axis of rotation of 3-fold symmetry, So, this is the body diagonal, these are the body diagonal, right, and 6 axis of rotation, 6 axis of rotation, of 2-fold symmetry, So, that passing through the middle of the edge of the cube, So, opposite edge passing through the opposite edge through the middle of this edge. So, 6 axis of this type one can get from the cube that I have shown you. So, total 13 rotational axis, having different fold of symmetry one can get for cubic system, cubic crystal. And for reflection I have reflection symmetry. With respect to reflection from a mirror plane of lattice points, if you get the exact whatever the image, reflected image you will get, which exactly will coincide the other half of the crystal. So, then we will tell that crystal have reflection symmetry with respect to that plane. Okay. So, plane I have shown that in case of reflection, probably once more I can just draw with respect to reflection. So, this one can choose one can choose the plane in the middle of the cube. So, this is the plane, if I this is the plane. Okay. So, you can have the image of this half, exactly it is the this other half. Okay. So, it has the crystal, this cube crystal has symmetry with respect to this plane, reflection plane, mirror plane. Okay. So, this type of plane you can get 3, right. So, opposite phase, 2 opposite phase giving one plane, other opposite 2 phase and this other 2 phase. So, total 6 phases. So, 3 reflection plane one can get. Similarly, plane through the body diagonal, plane through the body diagonal okay. So, plane through the body diagonal okay. This is the plane, through the body diagonal. So, this is the plane. So, in this plane this half okay, this half will be so other half is just exact reflection of this half okay, with respect to this plane. So, other half just top face if you consider, then exactly you can. So, it is this plane. So, you will get this, and this point itself will be here, this point itself will be here. So, just connect them. Okay. So, that is the reflection symmetry of this cubic crystal with respect to this plane. And I told that this type of planes from each opposite face you can get 2. So, this is one and another these 2. So, okay. So, you will get 6 from each set of opposite face 2. So, you will get 6 symmetry plane. So, total you will get 9 reflection symmetry in cube crystal. So, 9 symmetry planes in cube crystal. So, total, so this all this rotational and this reflection, these 2 together is giving basically 22 symmetry element, for cube crystal. Okay. Here I have to just taken cube crystal, so that is why this is the number. For any other crystal one has to find out, and one can show that that number of crystal symmetry element will be very lower than the cube one. Cube has maximum symmetry, hexagonal have also maximum symmetry. Okay. So, then inversion. What is inversion? Inversion symmetry. Inversion symmetry is basically if we have a, let me draw here a cube. In case of cube, let us find out in case of a cube. Okay. So, in this cube, so one has to find out a point with respect to that point. If you just with respect to that point, I think I have to, with respect to that point here, just let me check. I will take this way. So, this opposite corner, this one, let me just, it's one has to find out the symmetric point is this, and then if I take this and opposite is this one, okay, basically body diagonal. So, and this will be opposite to this, no, this will be opposite to this, okay, sorry. So, this will be opposite to that is that corner opposite, yes. So, this will be opposite to this, and this will be opposite to this, yes. Okay. So, here what I have done, let me tell you, I think I have, yeah. So, it's yeah. So, this is a point if I choose at the body center. Now, you have lattice point. If you just take a vector joining this lattice point with this point, okay, if this vector is R. So, in this crystal, if there is a lattice point, exactly at minus R, okay, then we will tell this crystal have inversion symmetry with respect to this point. Okay. So, it is not only this point, only these 2 points, it has to generate all other point also with respect to this one. Okay. So, that is why I have drawn this. So, this with respect to this, you see, if this is the R, this is the R, so exactly there is another point at minus R. Okay. So, for all point you can all 4 points. So, this point have another place. Similarly, this point you can show it's exactly. Okay. So, inverse symmetry is telling basically, if I tell just this crystal have inversion symmetry with respect to the body center. So, immediately if I take a point, lattice point at this here, so there must be another lattice point at this point here. Okay. So, that is telling symmetry is telling. Okay. But here this, since cubic crystal we have taken known where the lattice points are there. So, it is easy now, easily we can see that, okay, yes, when this point exists in cubic crystal, this other point will must exist. Okay. So, that is the, so already, so this cubic crystal. So, this is called inversion symmetry. Okay. And this cubic crystal have only one point, one point of symmetry. So, if I add this one with this 9 plus 13, so total 23 symmetry, total 23 symmetry element for, and this all three whatever I have discussed, rotational, reflection and inversion symmetry, this is with respect to point, this is with respect to plane and this is with respect to line. Okay. For all cases you can see this crystal is itself in space, it is at one place, it is not going to the other place. Okay. So, it is in one place, okay, just rotating, okay, or I am generating just seeing this symmetry with respect to inversion. So, I am not, so it is not covering the space. Okay. So, these three together, these three rotational, reflection and inversion, this symmetry together and their combination, they are called basically point group symmetry, point group symmetry, point group symmetry of the crystal, point group symmetry of the crystal. Okay. So, for crystal system, so total this point group symmetry, total number of point group symmetry is basically is 32. One can show that there are only 32 point group symmetry, and all crystals whatever the structure, either cube or hexagonal or tetragonal, all crystals will show only these 32 types of group symmetry, point group symmetry. Okay. And another symmetry is called space group symmetry. Another symmetry is called space group symmetry. So, with this symmetry point group symmetry, so if you add basically translational symmetry, translational symmetry with point group symmetry, Okay. So, this will give symmetry in space. So, that is called basically space group symmetry, Okay. So, translation symmetry is with the point group symmetry. So, point group symmetry, so as I told this 32 types or 32 number, okay, with translation symmetry. So, if you combined, take combination of them, different combination of them. So, one can show that, one can see that there are 230 space group symmetry, So, all crystals have maximum this number of, not this one crystal will have this. So, all crystals whatever the space group symmetry will follow. So, it will be out of this 230. We do not need more than 230 space group symmetry to find out the symmetry of all crystal system, right. And basically this Brevis lattice, it follows this, it shows this 230 types of space group symmetry. Okay. So, this is about the symmetry of crystal, and this is the elementary preliminary concept of symmetry and but this is a very vast subject. So, in this for undergraduate course, this we do not have scope to explain more about this crystal symmetry. So, that one will learn in higher class. So, I think whatever this I have told you. So, that is enough for undergraduate course. So, this next I would like to discuss about the unit cell. Already you know what is unit cell. So, this is the smallest, this is the there is the pattern unit, that the unit repetition of which one can form the crystal, Okay. So, basically two types of unit cell that I have not discussed. So, unit cell. So, basically two types of unit cell. One is primitive unit cell, and another is non-primitive cell. Another is non-primitive cell. Okay. So, very frequently we use this term in solid state physics. So, non-primitive cell, and it is sometimes it is called conventional unit cell, conventional unit cell. So, primitive. So, let me take example of simple cube. So, it has three type of unit cell. Okay. So, it has this say this a simple cubic crystal. So, that means it has 8 corner, and in each corner there is a lattice point. Okay. So, here we have I have shown you that this number of lattice point per unit cell is 1. So, how it is that I explained. So, I have one this one you see this cube 8 corner. So, each corner have the lattice point. Now, you can see here just it is 1/8 portion of the lattice point for this cube. So, that is why from each corner, because this is 1. So, next from next half it will come 1/8. So, other side it will come 1/8. Okay. So, this 4 will give half, and this on top it will give again half. So, it will be 1. Okay. So, this is the just 1 unit cell per cube. So, here one can say. Okay. In case of say FCC, in case of FCC, I think on this plane one, and in this plane one. Okay. So, you will have this you will have I think no, not this one. Oh, so this type of, okay. So this type of so on each face, right. So it will share with the two. So half per from face, half per cube per unit cell. Okay. So you have 6 faces. So 3 and 8 corners. So again 1. Okay. So total is 4 unit cell. Total is 4 unit cell for this. Total is 4 lattice point per unit cell. This for FCC, and similarly for BCC, you have in middle, apart from this 8 corner, okay, from this 8 corner, okay. So that's the this type of, I think this, okay, in middle one, so it's 1, and this from 8 corner 1/8, okay. So this in case of 2, in this case it is 2. So it's 1, this 4 lattice point per unit cell, and this is 2 lattice point per unit cell, okay. So this is the, so what is primitive cell and what is non-primitive cell? So this primitive cell is defined as the smallest volume of a smallest volume of unit cell which will have 1 lattice point per unit cell, then it is called the primitive cell. If unit cell contains more than 1 unit cell, 1 lattice point, okay, per unit that unit cell, so then it will be called non-primitive unit cell, okay. So primitive unit cell, fine. Non-primitive unit cell is called conventional unit cell, and non-primitive unit cell, conventional unit cell generally used very frequently. Reason is that it is not that it is FCC, it is not that one cannot find out the primitive cell from this. Yes, one can construct the primitive cell from FCC, from BCC. So we do not need to use this unit cell, FCC unit cell or BCC unit cell. Only one can use the primitive cell also. One can find out for any crystal, one can find out the primitive cell, okay. But we prefer this Brevis lattice, because of symmetry. If you for this lattice, if you find out the primitive cell, this primitive cell will have different angle axes and lattice constant, quite different from this cubic cell. So you will lose symmetry of the crystal, okay, and that's why it's very important to choose the unit cell, even if it is conventional unit cell, but that is preferable for having higher symmetry. So that's why so choosing the conventional unit cell, non-primitive cell, it is related with the symmetry, crystal symmetry. When there are some unit cell will have more symmetry, that will be more convenient to study the crystal structure, the property of the solids. So that's why, because of symmetry, one use conventional unit cell, okay. So so if we have any, one can construct, there is a method, one can construct unit cell, primitive unit cell from any lattice. So what one has to do is taking one lattice, so just connect other, just connect other, whatever the lattice points are there, just connect them, okay, just connect them, okay. So in the lattice in 3-dimensional lattice, whatever the lattice point surrounding of this point are there, so just connect. Now, just take the normal bisect of each line, normal bisect of each line so one can see this, I think this no, this I think this so this bisect basically this covered a volume, covered a volume in 3-dimension covered a volume, and which will be the smallest volume and will have a only one lattice point per unit cell, that unit cell, this is the one lattice point, and then this unit cell is basically primitive unit cell, and it has special name who discovered this process. So, Wigner sees unit cell, primitive unit cell. Okay. So, this way one can construct the primitive unit cell whatever the lattice factor. Okay. So, this about the unit cell of whether it is primitive type or non-primitive type. So, non-primitive type is called conventional unit cell, which are basically used because of symmetry. So, in case of cube, this SCC simple cube is primitive cell, whereas the FCC and VCC are conventional unit cell, but these are preferable because of symmetry, but from this lattice one can construct the primitive unit cell. That's the primitive unit cell, but it has less symmetry. So, that is why we do not prefer this non primitive cell for this, but rather we prefer this conventional cell FCC and BCC. Okay, so I will stop here. Thank you very much for your kind attention.